Hello, good morning. So, this presentation is about how we can use high lift devices to ensure that the aircraft you're designing is able to fly at a very high angle of attack. So, essentially, it's a high angle of attack design for combat aircraft. So, overview of the presentation modern combat aircraft requirements are agility and maneuverability, ability to fly at very high angles of attack, high sustained and attained turn rates. This presentation focuses on design of high angle of attack flight with a case study of a combat aircraft. Two types of highlight devices are in use, namely leading edge LE and trailing edge TE devices. These are used in commercial aircrafts to increase the CL max in order to reduce the takeoff and landing velocities. Trailing edge devices typically increase the CL at zero angle of attack. Leading edge devices, on the other hand, for example slats, delay the onset of stall. There is an upward extension of CL versus alpha curve along with the initial slope. So typically, if you look at any kind of high lift devices, it changes the camber of the aerofoil or the local aerofoil. So adding camber at aft camber at the rear part of it, lift at a constant angle of attack is increased. It also produces a significant nose down pitching movement that must be trimmed by downforce on the horizontal tail. And that what happens is if trailing edge device shifts the CL alpha curve like that. So for the same angle, you get a higher CL, but it does not change the angle of attack at which the wing airfoil stalls. Adding nose camber does not increase the lift at constant angle of attack. However, it increases the maximum lift. So you can see this dotted line has changed this way. It has not changed the CL at lower angles of attack, but now the stalling angle has changed. So let's look at why this happens this way. So if you look at a typical trailing edge device like a flap, trailing edge devices such as trailing edge flaps are responsible for altering the zero lift angle. So you can see the CL alpha curve is shifted this way. So for the same angle, you have a much higher CL, but the angle at which the stalling happens is not changed. The reason is stalling happens because of what is called the maximum suction peak or minus CP. This is delta CP maximum. Because after this, the flow is going downward and it is at an adverse pressure gradient. So if this peak increases very high, then the flow is not able to follow the airfoil contour and it separates and leading to stall. So what happens if you have a trailing edge flap like this, which I've shown in red color here? It does not change the CP distribution at the front, but it does alter at the place where it is deflected. So you have the now red curve. So what you see is additional area on the delta CP, increasing the CL. So that's the reason it does not change the stall angle, but it does increase the CL at different angles of attack. That does not significantly reduce the suction peak. As I said earlier, suction peak is what leads to the stalling. So if it does not reduce the suction peak, stalling angle doesn't change, as you can see in this curve. Now let's look at the leading edge device. What does a leading edge device do? Leading edge device, as I've shown in the red here, actually reduces the CP max or the suction peak and shifts it downstream. So what really happens is you lose a little bit of say a lift here, but you gain that lift this place. But because the suction peak is lowered and shifted, so what really happens is the stalling is postponed. So the aircraft can actually operate at a higher angle of attack before it experiences stall. The leading edge device do not have a significant impact on the zero lift angle. So I just shown a zero lift angle for unsymmetric airfoil. Otherwise, it would have been passed through the zero angle of attack here. So now let's see how this thing can be used in trying to design a combat aircraft wing to increase its angle of attack, no, high angle of attack behavior. For any given planform of a wing, namely span, area, sweep, and thickness to chord ratio distribution, a wing has an angle of attack critical above which flow separation happens, and this is worsened by the leading edge sweep and the cross flow. So during preliminary design, we try to maximize this angle of attack critical to get required performance. Typically, that's the maximum CL, maximum L by D at different altitudes, turn rates, sustained turn rate and attained turn rates, and also acceleration at altitude. So this is what is being initially done in the preliminary design phase. So how do we manage separation with leading edge slats? The design variables we have in our control are wing twist, thickness to corridor distribution, that is from the root to tip, high lift devices, leading edge and trailing edge devices. Iterations are usually done on a clean wing alone, initially to start with, later with the wing fuselage combination. Several iterations are needed, 40 to 50 typically, before an acceptable wing geometry is obtained with an acceptable high angle of attack behavior. So starting platform also may need to change it, meaning that you may need to change the sweep angle, wing twist, the trailing and thickness to chord distribution and all that before you get an acceptable wing. So managing flow separation with leading edge slats, with time and cost constraints, tunnel testing for these many models is not feasible. So CFD tools typically are a good alternative and can be used to arrive at least 2 or 3 configuration, which then can be verified with wind tunnel tests. Separation basically, as all of us know, is a very complex phenomenon and difficult to capture. It involves several factors, example, turbulence, cross flow, low pressure gradients, etc. So if you look at a case study now, I'm not saying which combat aircraft, it's a combat aircraft case, generic case study. Experience has shown that the CP max minus CP max or the suction peak is a good indicator of a onset of separation. Many design houses have their own indicative thumb rules which tell them that locally in the wing, if the CP has reached this value, then separation is going to start from there. If we don't have in-house thumb rules, what we can do is we can use commercial CFD code or any indigenous code, for example, RANS, Reynolds Average Navier-Stokes, and typically with Spallart-Almaraz turbulence model. The reason I'm saying this because it's one equation turbulence model, and you have a less number of runs to be able to do. Of course, there are better turbulence models, but this is in the initial stage. So what we need to do is establish a correlation between delta negative CP max or the section peak predicted and flow separation, because in CFD code you'll be able to see flow separation and also the predicted CP max. This way, any design house can establish their own thumb rules, which tells them at what section peak the separation is going to happen. So let's look at a case study now. First step is to define, let's say, a symmetric NACA 64 series 4% thick airfoil of 1 meter chord. 4% because, as I said, it's a combat aircraft, and all of them usually are 4% or less. Because any higher would lead to terrible, drags at subsonic or transonic conditions. So typically, 4% and less is what is used in a combat aircraft airfoil. Use CFD code as I mentioned. RANS is a turbulence model with a high resolution mesh because it's only airfoil. You can afford to do that. You can have multiple runs with a 2D. Scan airfoil angle of attack range between -2 to 10 and locate the lowest angle of attack at which separation is observed. Because it's a CFD code now, you can actually observe this separation. This is the angle of attack critical for that airfoil, which is, of course, started with the symmetric airfoil. Then at that point, you identify what was the suction peak predicted by the code at that angle of attack. If possible, you can verify with slightly different turbulence models to confirm the no, CP max, the suction peak, and the separation. Now, step two is define new airfoils with leading edge slats. Again, maximum 20% chord, nobody goes beyond that, with varying deflection 5, 10, 15, 20, for example, not more than that. Repeat the first step basically to verify what happens to the CP max for the same airfoil at different deflections of slat. Obtain the optimum maximum deflection angle at which you give the highest angle of attack, critical angle of attack. For example, a symmetric airfoil, if it was stalling at around 10 degrees, a 5-degree slight deflection may increase it to 12 degrees or 13 degrees and slow slightly. Beyond 20 degrees deflection, there is no point of no return, so not much of benefit is given. So the next step, you start with a symmetric wing with the required leading edge sweep, whatever your combat aircraft, which sweep angle is based on the Mach number and for a representative area. Scan the angle of attack range between -2 to 10 as mentioned earlier. Locate the angle of attack critical and the span location at which the separation is observed first. That may be anywhere between the tip or the root. So that's what you're trying to identify. Identify the negative suction peak, which widely predicted by CFD at that angle of attack critical. Now again, you can verify with different turbulence modes. But now, of course, you are doing a 3D computation, so you need to be a little careful on how many runs you're going to make. So the last step is to define a wing planform with 2 or 3 leading edge slats, maximum 20% chord, as mentioned earlier, with varying deflections 10, 15, 20 degrees. Repeat step 3 to verify CP value. Obtain the combination of angles which gives the highest overall angle of attack critical. If this angle of attack meets the CL and L by D max requirement, you can freeze the model for wind tunnel test. So you may have to get 2 or 3 models for wind tunnel test, which can then be used to confirm your estimation. So here is a case of a combat aircraft. You can see the slats here. More or less, it's a symmetric wing, very little camber. You can see the slats, maneuver slats. Now here I'd like to mention that slats are also used in commercial aircraft, but in that case, they are used basically to increase the CL max and to reduce the landing velocities. Whereas in combat aircraft, slats are used basically for increasing the angle of attack during high angle of attack maneuvers, especially no, very steep turns, because that depends on the maximum CL. So they are usually maneuver slats, and during normal flight, these are retracted to reduce the supersonic drag. So here are some references based on which I have done that, and also typical preliminary design documents, internal documents of different aerospace companies. Thank you for listening to me, and please leave your comments on the blog space or whichever way you want to do. Send me a mail. Thank you.